Ladies and gentlemen, good afternoon. It's a great pleasure to be here. I'd like to welcome you to our workshop this afternoon about Bayesian networks in BayesiaLab. As we start, I'd like to give a special thank you to Stephen Tilley from Northwestern's McCormick School of Engineering, who was so kind to arrange this event this afternoon. So, also before we start, I'd like to introduce Dr. Lionel Schoof, here to my left, to your right, who actually will join me here at the podium and do portions of our presentation today. He will also be teaching a 3-day course on Bayesian networks in BayesiaLab that starts tomorrow. And yeah, Lionel just flew in from France yesterday, so please forgive him his jet lag in his presentation. So what are we doing today? I would like to start off with just the very basics, like, okay, why in the world do we build models? And how does that relate to the Bayesian network paradigm? What is the connection there? And then to go further, well, how does all that relate to artificial intelligence, which is obviously artificial intelligence a very hot topic these days. And then once we cover that topic, we'll move on and talk about the BayesiaLab software platform, which is obviously what we represent, what we promote. And there, we want to very quickly get into a number of examples so we can show you how Bayesian networks actually work in practice and can help you address quite a number of research problems. So, and of course, towards the end, we'll also make sure we'll have time for questions and answers. So for the most part, I'll probably cover the first portion, and then as we go to the examples, Lionel will take over the presentation. So, what is a model? And this may kind of sound like almost stating the obvious. A model is a simplified representation of some aspect of the real world. It can be mathematical, it can be mechanical, a representation of a process, of a system, of a sequence of events, etc. I put up this picture of a model because it's different than the typical models we see. Typically, we see apps on our iPhones or models in our computers. What's special about this one here is that it's a mechanical model, and it's a model of our solar system. And as you crank the thing, the planets revolve around the sun. And what is really attractive about this particular model is that you can look inside. You can actually see how the gears turn. You can literally see the function that connects all these planets. And that is actually quite a nice metaphor for Bayesian networks, because unlike many other models with a Bayesian network, you can really look inside and see what's happening, what's connecting the individual variables. But we'll come back to this later. Now, why do we want to build models? Perhaps the first thing that comes to mind, we want to build models because we want to predict. And one example here, again, an obvious example, is perhaps an insurance application where the insurance company looks at you and looks at your profile, your history, your driving record, what have you, and they want to figure out how much of a risk you are. What is the likelihood of you causing an accident or getting sick, etc. But one thing that is not part of the insurance company's interest is, well, how all this links together. Like, you may be asked a question like, are you a smoker when you apply for car insurance? They may ask you, what color is your car? And you may have a red car. And the insurance company may conclude owning a red car and being a smoker increases or changes your risk profile. They don't really want to know how exactly that works. They just want to establish that is the case. So that's a very pure form of prediction. Another typical prediction is when you look at financial data, for instance. We want to predict the stock market. We want to predict the movements of indices, etc. And what's interesting, again, about these types of predictions, that they are not really using a lot of external information. For instance, here this is an ARIMA time series model. There's really nothing structural that we can interpret about it. It's simply a model that is kind of derived from the history of data and then projects in the future. But we can't use this model in any way to understand what exactly is happening. So that kind of covers prediction. Let's now move to a different area. This is a recent graduate from Northwestern University entering the real world of business, managing a company, and he has all these buttons and levers to work on, and obviously he needs to know what is happening. How does this system work? So beyond just knowing prediction, this individual needs to know, well, what's behind it. He needs to have a representation, a model of the domain he's trying to influence, so he knows what lever to pull and what button to push. And so one way of representing such a domain, one way of answering the questions of how, is building a structural model. And what we see here, for instance, is a structural equation model showing pathways leading to pre-diabetes condition among patients as a function of a number of factors, such as what do we have here? Physical activity, socioeconomic position, diet, family history, etc. So this is a model that explains how lots of factors belong together with the intention of explaining why things happen. Now, again, all this may sound very obvious, but there's an important point to remember, and there are two papers that have really spelled this out in great detail. And these are the two papers by Leo Breiman and Galit Shmueli, and they talk about really what is so fundamentally different about explaining versus predicting. Not just in terms of the objective, but also about how models are created. And let me just illustrate it that way. They really explain how a model that can be very, very good for predictive purposes can be a terrible model for causal explanations and vice versa. So bear that in mind. And now let's get to the question of, well, where do we get our models from? What is the origin of models? And perhaps for the longest time in the history of science, theory has been the source of models. So what does that mean? Let's use this example here. Let's use an example from the field of marketing science, where we're always interested in, well, how do people choose? How do they choose products and services? How do they choose transportation, etc. And for some time now, for several decades now, the logic choice model has become a very popular form of model that is used to, with whom scientists use to model choice behavior. And what that means is basically we have, here on the left-hand side, we have this little graph panel. And this theory basically says our choice probability is a function of the utility we perceive. And as the utility on the x-axis increases, the probability regarding this particular service or product, the probability of purchase will increase. But one part of the theory here is that we have a logistic regression that says this is the function of how the choice changes as a function of utility. But this is pure theory because we haven't derived this. Somebody could argue, well, that should be a linear function, or that should be a squiggly line. We don't really know. But the theory, the proposed theory is, it is a logistic regression. So that's just one type of theory that is very often employed. So, but what else do we have? What's really a big topic these days is data. Everybody is talking about data for several years now. And we're talking about bigger data, terabytes of data, petabytes, and so on. And a lot of people think that's like we can solve all the world's problems with just more data. And as you will hear us talk about these things, you'll hear a bit of a cautionary note. as we explore this, because we don't think big data can answer all questions. And even though today a lot of people may think, who needs theory with all the data we have, I think we'll show that that is an incorrect approach. Anyway, so let's go to this representation here, to this graph. What I've now done is I've put together both the modeling purpose, the modeling objective, that's shown on the x-axis, and then on the y-axis we have the model source, where models come from, how we develop them. So here on the x-axis, on the left-hand side, we have association correlation, which relates to description, prediction. As we go to the right here, we look into causation, which relates to explanation, simulation, optimization. Generally, things that we could relate to reasoning. And then on the y-axis, we have at the bottom theory as a source for the model, and at the top we have data. So with that, we really have 4 quadrants that can delineate the field of modeling. And as I should also add, all models are wrong and some are useful. So this is obviously a highly simplified representation of the world of modeling. But for the purpose of this presentation today, I think it's helpful to kind of think in these quadrants. And now if we look at existing fields of study, we can, for instance, position the social sciences, economics, epidemiology. We could put those in the lower right-hand quadrant. They're usually based on theory, and in those fields we're often interested in causation and how things happen, how interventions will happen, etc. As we then go further to the right, there we have the fields of operations research, where we didn't really get into simulation and optimization, so we can determine what's the best way to deal with complex systems, etc. In the upper left-hand corner, on the other hand, we have models that are really all about association, correlation, and prediction. And nowadays, many of those are strictly based on data. And perhaps one of the best examples is the recommender engine that you'll find in Netflix, or perhaps the recommender engine in Amazon. They work remarkably well, and they perfectly well explain what Lionel wants to watch tonight. But the thing is, you can't open up those recommender engines and look inside and see how and why and how all this is connected. They're rather statistical devices that give you a recommendation, but there is nothing that could tell us what would make Lionel watch a particular movie. It's just that here's what it is. Here's our prediction. An example of a modeling type that actually uses theory and goes into the explanatory area is a whole discussion about global warming and climate change, because there very much many scientists have developed a theory basically saying, okay, here's we have certain causal connections between CO2 and the atmosphere, etc. And if we use this theory, fit that with data, we can come up with a model that perhaps explains the climate change. So, but why am I showing this? And this goes back to what I said earlier when I referenced studies by Breiman and Shmueli. We need very different modeling techniques for each of these quadrants, really, which for researchers, or well, for academic researchers, perhaps, well, that's fantastic. It's a lot of fun to explore all these domains with very specific techniques. For the applied researchers, for analysts, for businesses who have to kind of analyze things for a living, that becomes a challenge, because you really have to have a specific type of modeling approach for every quadrant that we show here. That's a challenge. So, and that's where we think Bayesian networks can come in, because Bayesian networks are really quite a remarkable modeling approach that can very nicely cover all these quadrants. So let me start here on the left-hand side. First of all, we can build Bayesian networks, both from theory. So if we have subject matter expertise on a particular domain, we can use that. We can directly encode that into a Bayesian network. On the other hand, if we have data and not any particular knowledge about the domain, we can apply knowledge discovery algorithms and perform structural discovery and represent these discovered structures as a Bayesian network. And perhaps most importantly, what we can do in a Bayesian network, we can include causal assumptions. And that's really quite an important point. We can use our expert knowledge about causality, introduce that formally into a Bayesian network, and then use a Bayesian network for causal inference. And that's really, unfortunately, we won't have enough time to really explore the topic of causality this afternoon. But this really distinguishes Bayesian networks from many other modeling techniques. In a Bayesian network, you can directly perform causal inference as opposed to performing observational inference and then applying causality as an afterthought. Causality can be an integral part of a Bayesian network model. So now, well, we haven't invented Bayesian networks. Rather, Bayesian networks were invented by Professor Judea Pearl, who has been studying the field of causality now for several decades. He's still researching today at UCLA. And in the mid to late 1980s, he has really coined the term Bayesian network. And since then, it has really flourished and developed into a very large field of study with dozens of books that have been published and thousands of papers. And yeah, Bayesian networks have really developed very nicely throughout academia, but it really has taken quite a while for those to move into the applied research. And that's part of our mission. We want to make sure that these very powerful attributes of Bayesian networks are accessible to applied researchers beyond mathematicians, beyond computer scientists. We want Bayesian networks to be leveraged by anybody who is performing applied research. So what exactly is a Bayesian network? I've just talked about so far what you can do with it, but what is it? Well, it's a graph. The graph is the model. In a Bayesian network, there are no formulas, there are no functions. What you have are just two very simple components. There is a component of a node, and then there's an arc. And that's it. That's really all you need to know. And even all this may sound very, very simplistic, you'll see what complex systems you can encode with just these two elements. Now, the first example of a Bayesian network that I want to show is a very old example. And if you Google Bayesian networks, you'll probably come across this textbook example. This is an example that was written about by Lauritsen and Spiegelhalter in 1988. And this example is about lung diseases. It's about patients, their symptoms, X-ray testing, etc. And it tries to sort of capture all the interactions between symptoms, the disease characteristics, etc. So let's now take that idea and build a Bayesian network on that basis. So let's start with our group of patients. Imagine you are a lung doctor and you have hundreds of patients perhaps, and you want to now describe your group of patients as a whole. You want to build a model that describes your patients, their symptoms, their diseases, etc. So we would start off with the first variable perhaps, and one that's quite obvious is perhaps a variable for the age of the patients. So the first node of interest, the first variable of interest is age. And in a Bayesian network, all variables are represented as nodes, which are like these, in our software, they're just these blue bubbles. So this first node is age, and you can see that this node has 3 states, basically patients under 30 years of age, under 65, over 65. So we have 3 discrete states, and in addition to the values of these states, we also have a probability associated with it. So we know, for instance, that in this patient group, 25% of patients are under 30 years of age. So very simple so far. Let's go to the next, add another node. The second node we add is smoker. It's a binary node that basically says, are you a smoker or not? And then we introduce an arc. And what this arc does, it relates the states of the node age to the states of the node smoker. And how exactly does it do that? It's done in a conditional probability table. So you need to envision that this arc in the background contains a table, kind of a crosstab, that relates the states of the variable age with the states of the variable smoker. And so we can read out, for instance, among folks who are older than 65, 74% are non-smokers. And now you might say, well, this is still very, very simple. I could do that in Excel with a simple crosstab. But you're absolutely right. That is still very simple. But if we now carry on and start to introduce additional variables, we could build something like this and introduce the node cancer, a binary node that says whether you have cancer or not, whether your X-ray came back positive or negative, whether you have bronchitis, dyspnea, tuberculosis, and then relate all these conditions with each other, all on the basis of what has been observed in this group of patients. So what is nice about a Bayesian network is that you can really capture the entire joint probability distribution of what you see in your patients in a single model. And in a Bayesian network, we don't necessarily have to distinguish between independent and dependent variables. We can rather say, let's just model all patients with a single, with a single network, and thus capture the entire joint probability distribution. I should also say, Bayesian networks, in the way we use them, they are non-parametric. They can represent nonlinear relationships, which is very important. They're probabilistic. And one special topic that I'll get to in a second is that what we can do is we can perform omnidirectional inference with a Bayesian network. And I'll show you now what this means. For instance, let's say we've built this network, and later on we'll show how exactly we can create one. For the time being, we'll just say we take this network as a given, and we want to perform inference. For instance, we want to know, given the patient age is greater than 65, we would like to know what is the probability of a patient to have cancer. So look at the top panel, highlighted in blue. There we have the marginal distribution of these probabilities. So there, for instance, the marginal probability in this group of patients to have cancer is like 3.9%. Now, we said evidence. We now focus, we zero in on the age group greater than 65. And now we move to the green panel. Now you see that 65 is highlighted here with 100%. And now we can read out the associated probability. And now given the age, the probability of having cancer has gone up to close to 8%. So this is the first type of inference. Now, in a Bayesian network, you can also immediately do the opposite. We can perform inference in the opposite direction. And let's reset everything, go back to the marginal distribution. We're back to the blue panel. And now, instead of setting evidence on age, we set evidence on cancer. given that cancer equals true, now what is the associated probability distribution on age? And again, we look at the green panel and we see now if cancer equals true, our proportion of older patients is a lot higher, which is quite plausible. So we've just done inference in both directions, and you may say, well, I could still do that with a crosstab and a pivot table in Excel quite easily, and you're right. But what in a Bayesian network, you can't just perform inference between two nodes. Inference always happens across all nodes. So even though I only highlighted age in cancer, whenever I zero in on any particular subgroup, the evidence propagates throughout the network, and the conditional probabilities across all nodes are automatically updated. So here, for instance, given that I have set cancer to 100% true, you see now all the updated conditional probabilities for all the other variables as well. So what that does, it really gives us an omnidirectional inference engine. We can, and I like to represent this as this kind of gearbox where you have all these gears, all these wheels interacting with each other, and regardless of where you turn, you see all the wheels, how they're interconnected and how they turn. You could turn here on the right and it propagates. You could turn here on the left and it propagates. So that's kind of a metaphor for omnidirectional inference. And this is really one of the key characteristics of Bayesian networks. So you may now ask, well, what does this have to do with artificial intelligence? And I really like the latest cover of The Economist, and especially because they took a picture of the back of the head of my friend Lionel here for their cover. I think it's really quite an honor to have you picture, or it could be Roman. I don't know. But so artificial intelligence is a really hot topic, and there are also quite a lot of sort of cautious notes that a lot of scientists are expressing about the dangers and risks of artificial intelligence. But we kind of want to, in a way, go back to the very basics. And instead of talking about machines that may take over the world, we want to talk about, well, how artificial intelligence on a very small scale can really help us to reason. So looking at the basics, what is artificial intelligence? Artificial intelligence means that refers to machines that can learn by themselves. It refers to machines that can hold, that can represent knowledge. And then it's about machines that can perform inference and reason. And now just bear these concepts in mind, and let's now take a look at this network that we just used, the network of patients, of lung patients. And if we think about what's contained in there, we have declarative and propositional knowledge, because it contains probabilities, it contains the values. We have associational knowledge. We can see how nodes are associated. And we can also have encoded any causal links, how specific nodes are related and causing other nodes. So with that, we do have a knowledge base. Additionally, the Bayesian network itself, and with the inference algorithms that, for instance, Professor Judea Pearl invented, a Bayesian network is an inference engine. So between the knowledge base and the inference engine, we really have a type of artificial intelligence. We have an expert system that we can query. And we'll see that later in Lionel's demo, how we can really use such expert systems in a very, very practical way to kind of expand our own reasoning capabilities. So, you may have used, many of you may have used Bayesian networks already. Here's an example. You may be familiar with WebMD. I use it quite a lot. Whenever something itches, whenever I cough, I wonder what it could be. So I go on WebMD and enter my symptoms. Given the symptoms I enter, this WebMD expert system asks follow-up questions. Well, do you also have this? Whatever may be related to the symptoms I've entered. And through a sequence of questions and answers, it then ultimately gives you a set of probabilities as to what you can have. Everything from a regular cold to the flu to lung cancer, perhaps. So it gives you the whole spectrum. So this is a major benefit for end users. Anyone, even without being a scientist, can utilize the knowledge that's contained in a Bayesian network, can utilize such an expert system. But even beyond the end user, Bayesian networks have a tremendous benefit for the researcher. And I'm just talking about experience because I used to work in the auto industry, and one of the things that I was doing was forecasting sales and market shares and economic development, and we would develop all kinds of formulas and regressions and time series models. And then usually the model we built would look something like what we have here on the left-hand side. Lots of Greek letters, and looks highly complicated, even though it actually isn't. But to the non-initiated, it may look rather threatening. So you'd go into a board meeting and present this, and people would say, yeah, we trust you, Stefan, that this is probably right, but there's no way for your audience to engage with the model you present. On the other hand, if you present a graph of a problem domain, a Bayesian network, anybody can really look at this and recognize the nodes, and see what is connected, how the nodes are related, and you can have a discussion. And even somebody who has no clue about modeling and regressions and what have you, they can say, hey, yeah, I can relate to this. This relates to my own experience, but they might also see, hey, something is missing, or there is an unobserved variable that should be connected, and so on. So we feel that this is a very important aspect, especially when you work in the consulting field. If you try other people to help understand their problem domain, you can much better engage with them about their domain than if you were to use some traditional research methods. So here's kind of the metaphor we like to use for that. With Bayesian networks, you really move from a black box approach to really we think of it like as this glass cube. You have a very transparent expert system where a lot of people can engage with you and actually help the researcher make sure that this approach is appropriate. So, sounds good perhaps, but now how do we get a Bayesian network is the next question. And I've already touched upon it a little earlier, the two principal ways of getting to a Bayesian network. The first is we manually encode our knowledge. We know about a domain, whatever it is, and we can simply draw nodes and arcs and thus encode our knowledge about how something works. And the second approach here is, and this is not to be taken too literally, this is actually not the approach we're using, but we have a machine discover relationships that exist in data. We perform knowledge discovery through data mining, and we'll also have an example for that in Lionel's demo. So, and this is really where we come in with our software platform. That's what we're promoting. We're promoting BayesiaLab as a platform that allows you to really build Bayesian networks, to edit them, to perform inference with them, to machine learn them, to analyze, simulate, optimize, all in the same environment, to really make that a one-stop shop for applied researchers. And what we also want to emphasize here is the lab part. BayesiaLab is a laboratory environment where it's a playground for the scientists where you can really dive into your problem domain, and through all the visualization functions and algorithms, you can really explore your domain, analyze it, build models, relearn it, recode things. So it is a very comprehensive approach to understanding complex domains. So in a way, what we've done is we've taken this concept, this mathematical formalism of Bayesian networks, and taken and expanded this into an entire research workflow that researchers can use. So basically, look at this from left to right. We can either build Bayesian networks manually through encoding knowledge. Here it is shown as expert knowledge modeling, or we can use machine learning algorithms to automatically discover networks. Once we have the Bayesian network, then that is the representation of our world, and with that we can analyze, simulate, optimize, diagnose, etc. From a very practical perspective, what this has done, this is what it's done to my life. I mean, I used to really, you can just go down this list, all these techniques, approaches, regressions, factor analysis, structural equation models, state space models, choice models, all these things I had in my toolbox, but in many ways, Bayesian networks and BayesiaLab as a software platform have more or less replaced all of those, because many of those techniques have their equivalent representation in the world of Bayesian networks. And that makes the life for the researcher a lot easier. And just to be a little bit more concrete about this, you may recall this quadrant graph that I showed earlier. What I've plotted now here on this graph, earlier I just showed that Bayesian networks can cover the whole spectrum. Now I've plotted more specifically what functions inside BayesiaLab kind of relate to any of these quadrants. And in Lionel's demo, we'll explore a few of these. Even though we'll, for the most part, talk about BayesiaLab today, there's several other family members in our portfolio of research software, one of which is the BayesiaLab Web Simulator. We'll have a demo on that. And then we have a couple of other tools in our toolbox, the Bayesian Market Simulator, which is a type of choice modeling tool. We have the Bayesian Expert Knowledge Elicitation Environment, which is a program that helps us generate networks and encode them even when we have no data whatsoever, when we have just expert knowledge available. And we're trying to bring this expert knowledge together in order to build a Bayesian network that becomes a representation of all the expert knowledge that is available. And then finally, we also have an API that allows you to programmatically access all the functions that we have in BayesiaLab. So let me just say a few words about us, about our company. Bayesian was founded in 2001 by two professors who worked in the field of artificial intelligence, Dr. Lionel Jouff and Dr. Paul Monteano. They're both still heading the company, and Lionel is obviously here today. The company has grown steadily from its very humble beginnings in this little town in 200 miles west of Paris, where it started in 2001. We now have a representation in the US, based out of Nashville. We have a team in India, and for some time now, we've also had an office in Singapore. We're actually, in a couple of weeks, heading to Singapore for a number of training events. So we're trying to spread the word about Bayesian networks. And even though we're still a fairly small company, there are more and more large organizations, universities that are embracing Bayesian networks and BayesiaLab for their research. Most importantly, perhaps I should mention P&G. They are one of our oldest and biggest customers in the CPG field. But then we have lots of consulting firms, market research firms. I think 5 of the top 10 market research firms use BayesiaLab. Technology companies, Dell, Microsoft, we have NASA, we work with the US Army. I mean, the point here is Bayesian networks are a very universal method. It's not limited to any particular field. So really it's everything from bioinformatics to risk management. And I think that's what makes it so attractive. And this is also one of the things we try to highlight in our annual conference, which, in case you're interested, will take place again this October in Washington, D.C. And there we have representatives from many of these companies, and we're trying to really share approaches. You know, something that works very well in the finance industry may work very well for insurance companies or in the aviation space and so on. So there's lots of interaction across these fields, and I find it personally very exciting to make these discoveries, how approaches that work in one industry can translate very well into solutions elsewhere. So now I've talked for quite a while, and now I think comes the fun part. We now want to see how this actually works. You'll probably say, hey, okay, we've heard enough, show us how this works. There are two specific examples that I want to pick out. Let's go back to our diagram here. The example 1 is about knowledge modeling. And then example number 2 will be unsupervised learning. And I think both, of course, we don't have time to go into everything, but those two, I think, become a very good, give you a pretty good feel of what can be done. Let me briefly describe example 1 before I turn things over to Lionel. And this is probably something we've all experienced. The question is, where is my bag? This is an example about knowledge modeling and reasoning under uncertainty. So now let me just briefly set this up for you, what we're trying to research here. So the question, imagine this scenario, and I think this is not at all contrived. I'm sure many of you have been in this situation. I certainly have. You have a tight flight connection here at nearby O'Hare. You're flying in, you're rushing to your next gate for your departing flight. You check in with the gate agent and ask, you know, I just came in, I raced over to the next gate. Will my bag make it? And the gate agent tells you, maybe. She says, perhaps there's a 50-50 chance that your bag will be on the connecting flight. And you say, okay. And you get on the plane, crossing your fingers. So then you get to your destination, and there you stand. You know, you've been there, I'm confident. So you wait, everybody's bag comes off the conveyor belt, lands on the carousel, and you wait and wait and wait. And at some point you start thinking about when is it time to actually go to the baggage office to make your lost baggage claim. And I've been in that situation so many times that I started thinking about, well, how could I solve that? As I stand there, as the bags roll off, and I don't see mine coming, what is the probability of my bag actually to still show up? Should I wait longer, or should I get in line at this long line of people who are waiting for the lost baggage office? So I think this is a great example of how we can use the bits and pieces of knowledge we have about the problem and use a Bayesian network so we can properly reason about this problem. We want to answer the question, well, when is it time to give up? When are my chances just getting too slim that my bag will just come off the conveyor belt? A small problem that seems quite intuitive, but actually you can't easily solve in your head. And that's where I think it's a great application of artificial intelligence, just a small step in terms of using artificial intelligence aids, but we'll show you how we can quickly use the information we have, encode the Bayesian network, and then provide an answer. So with that, we'll do a quick swap here of computers and microphones. This is still green. Mm-hmm.
Okay. No. Did you change the resolution? What is that? Is the best one? Which one did you use?
Okay, good.
It's not so big. Too big, no? Okay, let's see. Okay. So let's start with the example Stefan just described with the bag. And so here is the software we are using, BayesiaLab. And the idea is to create the graph manually, right? Because we don't have any data, we just are going to use our expert knowledge on this domain. Well, so the first thing we have to do is to create nodes, right? Because as Stefan said, a Bayesian network is made of two parts, a graphical one with nodes and arcs, and then a quantitative one with probability distributions. Right? So we will start by creating a node. And this node, this is our first dimension, is my bag is on a plane. Oops. Okay. So this is the first dimension, and this is indeed our variable of interest, because this is what we want to know, right? And as Stefan said, right now, after speaking with the gate agent, we just have a 50-50, right? So we don't know anything. We just know that, well, we have 50% of chance to have our bag and 50% of chance not to have it, right? So this is a prior. Then we have my bag in the carousel, on the carousel. So this will be the second dimension. And it also contains, this node contains also two states, true or false, right? And we know that we will have a connection here from this node to this node. We are just indicating that we will have a probabilistic link between these two dimensions. But now we also need to take into account a third one. And this third dimension is the time, right? So we are going to create a third one, which is a time. And this one, you know, by default, when we are creating a node, we have two states, true or false. But this one is more a numerical value, right? So we are going to create 10 states, or 11 states here, from 0 to 10, right? And indeed, these are, if you want, just minutes. So we are going from 0, from start, and then till 10 minutes. So we are just hypothesizing that, or speculating that we will receive, all the luggage will be delivered in 10 minutes, right? And with a steady rate, so 10% per minute. So this is the time dimension. Now we need to define what is the prior on this dimension, and as we don't have any knowledge on this, we will just start with a uniform distribution, right? And we now have a link from time, then my bag is on the plane, and these two dimensions are defining the probability that we will have the bag on the carousel. I will not have enough space. Okay? So we now have to define the most important one, which is this one, my bag on the carousel. So if I double click on this node, this is my probability distribution. So for the first two nodes, we don't have any incoming links. which means that we just have to use what we call marginal priority distribution. When we have incoming links, as this is the case for this one, we have to define conditional priority distribution. So what is the priority of having the bag on the carousel given the time and the bag on the plane, right? So we'll have to define this priority distribution where we have 22 cells, 22 distributions, right? So the first 11 ones will be quite easy. If the bag is not on the plane, we can be sure that it will not be on the carousel. So we just select the 11 first cells and hit return. And now we are just indicating that if it's not on the plane, it will not be there, right? And then, so we can select these 11 one and hit complete. So the first part is done. Then the second one is, what is the priority at time step t0 that the bag will be on the carousel? Easy. It will also be 100% false, right? When we would start, there is no bag. And then we will consider that we have a steady rate, and as I said, 10% per minute. So the first step, it will be 10% of chance. Then after 2 minutes, 20%, then 30%, 40%, and so on. And after 10 minutes, if the bag is on the plane, we can be sure that it will be on the carousel, right? So I just have now to complete everything. And I have my conditional priority distribution, right? So I can do that by populating the table by hand or by cell per cell, or we can also use equation, right? So for example, I can say, I can describe this table by using an equation. So it will be a probabilistic equation. And I will just have to say if my bag is on the plane, so this corresponds to this set of cells, right? And then I need to describe this one. So I need to say, and if this is true, so then if my bag on carousel is true, so I don't have to add is true because it's a Boolean variable, then what is the priority? It's just 10 time time. So when it's true and when it's false, I have to describe this. It will be just 100 minus 10 time time. Else 100 minus 10 time time. Right? So this is the first part. And then I need to describe this one, so which is else if my bag on the carousel, then I can be sure it's 0, and otherwise 100. Okay? And then, by using this formula, I'm able to generate these tables. I can remove everything, right, and go to equation. And now everything is back, right? So you can describe your expertise either cell per cell or distribution per distribution or by using equation. And you can also go to Excel, enter directly something in Excel and paste it here, okay? So this is done now. So we have our first Bayesian network. And now that we have these 2 dimensions, these 3 dimensions plus the links, we have a perfect representation of the joint priority distribution that is described by these 3 dimensions. So we have a cube, and inside this cube we have probabilities everywhere, and the sum of all these probabilities of inside the cells here is equal to 100%. And we will be able to use this network as a probabilistic expert system, if you will. So now I'm gonna just open this panel, and I can associate, monitors with each node, each dimension. So I have my target node, because this is my node of interest here. I want to know if my bag is on the plane. I have what I can observe. Is it on the carousel or not? And the time. So arriving at the airport, at time step t0, I'm going out from the immigration, and I can see that, well, my bag is not here right now at T0. So I have, as the gate agent, 50% of chance to have my luggage and 50% of chance not to have it, right? And then, as the time increases, so after 1 minute, let's suppose my bag is not on the carousel, then the priority that is on the plane is decreasing from 50% to 47%, right? And then after 2 minutes, it's 44, and then 41, and so on. 9 minutes, it's 9%, so I can start to cry. And 10 minutes, it's over. It will not be there, right? So we can go through all the states, or we have some tools like that, where we will be able to describe the evolution of these probabilities, right? So given that my bag is not on the carousel, and I can see how the priorities are evolving with the time, right? So this is one way to use this model. Okay? So when I do that, so setting, I can, as Stefan said, we have this omnidirectional inference, because if I set evidence on my bag is not on the plane, this is, oh, sorry, not on the plane. I'm just simulating, and then the information is going toward this one, and I can be sure that my bag will not be on the carousel. So this is simulation from a root cause to a symptom. I can do here, this is kind of diagnosis. If my bag is not or is on the carousel, I can be sure that it was on the plane. And I also have an update on the expected waiting time, right? And we can also do intercausal reasoning with both a symptom and a cause in order to update the priority here, this one. Okay, so we have these three types of inference in this simple network. So I don't know if you have any questions so far. No? So let's now speculate that we have somebody, a colleague in the plane, who had the exact same first flight, right? And so we want to know if, when we, probably you have experienced that, you are waiting for your luggage, and then you see somebody who was on the same plane and he's getting his luggage, but yours is still not there. So what is the impact of this observation, right? So we just have, in this case, to copy these two, paste them, and because it will follow the exact same priority distribution, right? So we have, let's say, this bag. Okay. So we have this network now. So by copying this, we have the exact same priority distribution for the carousel. And now we have also a link between these two nodes, right? So this is, let's call that, percentage of process during transit. So this will just indicate, if given the time between the two flights, what was the percentage, what amount of luggage they were able to process, right? And we will have a connection between these two, like that. And this one, we're going to create 11 states from 0 to 100%, right? So if there is enough time, they will be able to process all the luggages. Otherwise, just a few percent. And so we don't have any clue about this. So it's a uniform distribution. And then we're going to use a formula for this one. So just so it's again a probabilistic equation. And we just say that if the bag is on the plane, then it's this. Otherwise, it's 100 minus this. All right? I just have this table. Okay? So now I can also copy directly this table and paste it here. So we have the same priority for the two guys. And given that we have this new network, so we can do the exact same thing. So what is after, let's suppose after 4 minutes, we still do not have our bag on the carousel. So we have a 37% of chance to finally have our bag. But if we just observe that our friend received his bag, then this priority is increasing to 58%, right? So the information, as you can see, is going back to this node, but also then via this path, we are also updating this node. So we have lots of paths here to update the priority distribution of the bag in the plane, on the plane, okay? And then the same thing we can, evaluate the priority distribution or the priority evolution of having the bag on the plane given that our friend received his bag, right? So this is kind of simple. And we can still add complexity. So I will just open this one. And so this one is, we have the same thing, time. But now I'm just considering that we have one guy who is a platinum member, and he has a priority luggage, if you will. And the other one, no. So he has a very basic one. And so I just change this one in order to indicate that as this guy has a priority luggage, so the priority is increased. So after 1 minute, he has 30% of chance to receive his luggage. After 2 minutes, 50, 70, 80, 85, and then going slowly to 100%, right? This one, as it has no priority, it will be 5% to receive his luggage after 1 minute, then 10%, 15%, 20, 25, so it's increasing. But we can see that he will receive his luggage, or the priority that he receives his luggage after the priority one is higher, right? And the same thing for the processing in between the flight. So depending on the time they have, they will first process the priority one, if you will, okay? Plus, I've just added a new dimension. You can also lose your bag. So it's not only the time to process the luggage, but also you can also lose your bag in between, right? And then you can also do the same kind of computation. So it's kind of so this is our variable of interest. We have a priority bag. And if after, let's say, 7 minutes, you still do not receive your bag, so it's false here, then the priority is that. So before starting, yes, let's see that. So we can see that with the priority, you have 72% of chance to receive your bag, and without 40% in this case, right? And then if let's suppose that after 5 or 7 minutes, you still did not receive your bag, the priority is 11%. But if you see that your colleague received his bag, so it's increasing to 27%, right? And then you will be able to do all these combinations to see if you are increasing a lot or not, given all these combinations, right? So you can really go through all these states, right? So this is one way to add complexity. So the more knowledge you want, the more dimension you can add in your model, right? And I want to just to show you how we can use this kind of Bayesian networks to also publish a model. So let's suppose you are quite satisfied with this model and you want to share it with the community, right? And so the best way to do that is just to use the web, right? So we can just go there and, we have the web simulator editor in this one and define what are the dimensions we are going to use as input nodes or input variables, and what are those we are going to use for output, right? And given that we have these two types of variables, then we can also define what types of objects we are going to use to input or output, or to display the input or output variables. So it can be switches, it can be drop list, it can be sliders, whatever. So we are not going to use all these. And the same thing for outputs, right? So once you have defined all these types to your variables, then you can go to this and publish your model. And here is, for example, this one. It's going to, okay. So you have here the nodes we are using as the input nodes, and these are the output nodes, right? And then you can directly, so let's say we are at time step t0, so you can be sure that you cannot have your bag here on the carousel at time step t0. You have the priority that you will finally get your bag. What is the priority that the other one will receive his bag, and so on. And the priority is that you will lose it or not, or you have lost it or not. And then you can increase the time to see what happens. So you still do not have your bag. The time is increasing, and you directly have the impact on all the output dimensions, right? And if your colleague receives his bag, then this will be updated. So you can be sure that they will at least able to process some luggage during the transit, and then you have all these updates, right? So this is now a good way to share your model without to have to explain Bayesian network. Once you have validated your network, you can just publish it. Okay? I don't know if you have any question on this. No? Crystal clear? Do you want to say a few words?
Let's switch again. I should add at this point, Lionel has platinum status with Air France, so he never loses his luggage. So, just. All right, thank you, Lionel. I think this was really an interesting way of how we can just take a few bits and pieces of information and without resorting to any elaborate formulas or statistical methods, just sort of put a few things together and then use that for very, very efficient reasoning. So, so that was knowledge modeling. Now I want to go to a different area. We want to go to unsupervised learning. And this is where we just take data without any knowledge, just look at data, and from that, with BayesiaLab's machine learning algorithms, discover structure. And the example here is a stock market. And the stock market is a good domain to study simply because there's so many time series that are available free of charge. So you can really very quickly collect great data sets that you can explore. And now, more specifically, what we want to do is we want to take a look at the day-over-day returns of all stocks in the S&P 500. So I've just shown like the first 16 stocks and showed their return over the 6-year period. And the objective here is now that we want to just look at these time series and see whether we can find any structure in this data. Let's assume we're aliens landing on Earth, picking up the Wall Street Journal, and we try to figure out, well, what is going on with with these stock price movement. Now, perhaps traditionally we would have approached this with a correlation table. Just imagine we could perhaps do a 500 by 500 matrix and see what the correlation is between all these stocks. One of the challenges is that first of all, it's a gigantic table, And then we also see everything is related to absolutely everything else. So everything moves together. We can use color coding and all kinds of things. And yet it is very, very difficult to really find any meaningful structure other than, well, everything seems to go up and down together, more or less. So what we now want to do is we want to take the data. We want to bring the raw data into BayesiaLab. We want to apply a discretization, then perform unsupervised learning, and then in the end we want to interpret that, see what we can see what makes sense, etc. And really, what will be interesting about all this is that we will create a single model for all 500 stocks, without input, without distinguishing between input and output variables. Just a single model for all the time series. And once again, omnidirectional inference will be a very obvious feature that we can observe here. So with that, once again, Lionel, come back. I'll hand you the microphone again.
Thank you. Oops. Okay. Okay, now, so as Stefan said, we have a data set that describe the day-over-day returns of all these stocks. So we are not going to create the nodes manually, but we are going to read the data set and then create one node per company, right? So now we just open the data source. It's a text file. And this is the S&P 500.csv, so it's a really classical CSV file. So we have on the first line the ticker symbol of the companies, right, to indicate what are the variables. And then we have 1,510 rows. So it's 1,510 days here. And we don't have exactly 500 companies, but just 459. So we just kept all the companies that were there during these 6 years. And as you can see, everything is continuous here. So this is the reason why it's in turquoise in BayesiaLab. And then we will have just to load this and define, because you have probably observed a few minutes ago, when we create a node, it has exclusive states. So it was true, false, 1, 2, 3, 4, 5, etc., etc. So it's, in BayesiaLab, it's always discrete, right? So as we have here continuous values, we will have to process these values to create discrete states. So this is what we call the discretization. So discretization can be done via different ways. So the first thing we can do is go to the manual discretization, have a look at either the repartition function or the density function. And as you can see here, it's almost a normal distribution with a mean of 0 and a standard deviation that we cannot just determine like that. And we can create, thresholds, define bins like that by setting threshold on this density function, right? So with this kind of normal distribution, we can say, okay, I'm going to use 3 states, 2 for the tails and 1 for the model value, right? So this is one way to do that. But then we also have some automatic discretization algorithm. We can use a density approximation, which is an algorithm that just analyzes density function and create automatically a discrete representation of this density function. We can use k-means. I guess you are familiar with this unsupervised algorithm. We can use equal distances or normalize equal distances and equal frequency, right? So for this one, we're going to use k-means in 5 bins, right? So if I use k-means in 5 bins, this is exactly what I'm going to have, right? And then so I have 459 variables to do, to discretize. So I'm just selecting all these variables and setting k-means into 5 bits, right? So we will carry out 459 k-means times 10 because we are trying different seeds. So this is what we do right now. And so in a few seconds, we will have a Bayesian network with 459 nodes. Here it is. So we have one node per dimension. We have the ticker symbol, which are not, I don't know, perhaps you are familiar with this, but I'm not really. So we have dictionaries, that, just simple text files that allows you to associate, properties, colors, images, name to these nodes. So I can just associate a dictionary of comments. And now I will have the name of the companies here. Right? And if I go directly to validation mode to have my monitors, I can have a look at this one. So this is advanced micro devices. Right? And by using the k-means discretization, we have the result here. So just by loading the data, we can see that we have, over the 6 years of historical data, 30% of the days corresponds to, has come to, yes, to 0, almost no variation at all, right? And 13.7 to a loss of 3.4% and so on, right? So we have this knowledge just by loading the data. But right now, we don't have any connection between these nodes. So we just have the marginal priority for each company, right? And the idea will be to find what are the links between these companies, right? So when we are learning a Bayesian network, at least the approach we are using is everything is based on information theory, right? So when we have this distribution, we can compute what we call the entropy of this distribution. So this is the amount of uncertainty of this entropy. And I don't know if you are familiar with that, but if you have a uniform distribution, this is exactly what we don't want to have, because this is the highest entropy, so highest uncertainty. So we want to reduce the uncertainty on the variable. So we are looking for something like that, right? So we want to be able to minimize the uncertainty. So given that I have this distribution, I know that I have an entropy of 2.24, right? So we are just using this distribution to compute this entropy. And then we will try to, for example, to add a link from this company to this one. And given that we have a link, we can measure if now, if we know the state of AES, we are able to reduce the uncertainty on advanced micro devices, right? So we know that we have 5 states for this one. So when this one is losing more than 2.8%, this is, as you can see, changing the priority distribution on AMD. And then we can compute what is now the new entropy of this distribution. So it's 2.08 instead of 2.24. And we will do that for all the states, right? So we can do that 5 times. And now we have an entropy of 2.08 again. So given that we have 5 new conditional entropies, we can compute what is what we call the mutual information between these 2 variables, right? And we will do that for all the couples of all the pairs of companies, right? To try to build a network that will minimize the entropy of the global system, right? So obviously we will not do that manually. We just have to go to learning and use one of the unsupervised learning algorithms that is available in BayesiaLab. And as we have just a few minutes here, and we have 459 companies, we are just focusing on the tree. So we just want to learn a network where we have the maximum number of parents will be 1, right? So it's linear in this case. So I'm just using the maximum weight spanning tree. And we are learning the relationship between the variables, right? So this is the network we can find. And as you can see, as Stefan was saying before, you can go to the board meeting with that and explain what you found, right? It's kind of easy. We don't have any formula, but still. So the first thing we can do is try to find a layout to try to find some explanation there, right? And still we have, so now we have a nice layout, more easy to understand, but still we have almost 500 companies there. So it's kind of difficult to understand. So we can try to zoom in, but if we zoom in, then we are losing the other part of the graph, so it's not easy. So we have a tool that will allow to analyze a little bit this network. And this is under node force analysis. So we are going to create a kind of mapping here. As you can see, it's much better. But we can directly focus on this. So what I'm just displaying here, this is the same thing. This is a Bayesian network. But now we have different type of information. So the size of the nodes is directly proportional to the strength of the company in this case. So the bigger the company is, the most important it is for reducing the uncertainty of the system. Right? So we can see that with this analysis, the most important company here is Simon Property Group. So if we have some insight on this node, then we will be able to reduce the uncertainty on a subset of companies. Right? And then the second one, and use this slider, is Packard, and then we have Dover, and so on. So we can go through the network like that and see what are the most important companies. So you can see, even if I have 459 companies there, I still can understand what are the main dimensions. So if you have 2,000 genes, you can also do the same thing and see what are the main important ones. Right? So this is one way to analyze this network. Another one is, once we have this, we can try to mapping. Come on. Let me. Is to try to, so by using this graph, to try to create some kind of clusters, right? So this is what we call variable clustering in this case. So if I were just to create one group, so all the company will belong to this group, and the name of this group will be Simon Property Group because this is the most important node, right? Then I can create two groups, and then it will be one with Simon and the other one with Dover, right? And then we can go like that and see what we can, how many groups we can create. So this is, I don't know if you are familiar with variable clustering. So it's really different from factor analysis because in this case we are not trying to create orthogonal axes, but this is like more, you know, when you have images with pixels, here it's like changing the zoom. So we are just identifying, oh, this group of pixels correspond to the face, this one to the legs, and so on. And then we are just changing the zoom, but we still have connection between these new dimensions, right? So this is a way to create factors, indeed. And if we go there, perhaps we can have a look at, oops. If we want just to see what are the connections that has been found, I guess you know these companies, you are living here, so you can see that we have the energy company here. We have, I guess we have, oops. Where is my favorite company? We'll have to find it. So if we are looking for Procter, for example, so here it is, and I guess you know this company, but it's directly connected to Kimberly-Clark, Clorox, and so on. So we can find Kellogg's and so on. So we can see that without any expert knowledge, just by analyzing these 6 years of historical data, we are able to find the ecosystem of Procter & Gamble, right? and the same thing for all the companies. So by analyzing these graphs, then you can say, oh, this is the energy sector here, this is a CPG one, and so on. So you can directly analyze this. And you can take, data coming from India, and we will have the same kind of result, right? So even if you don't know anything, then you will have useful knowledge directly. So the thing is, perhaps to conclude on this example, is those links are not causal, right? So I can see that I have a connection between Proctor and Kimberly-Clark, but this does not mean that if I'm able to do something to increase the value of Proctor, I will increase the value of Kimberly-Clark, right? This is just based on association. So we can observe that during these 6 years, when P&G is increasing, then Kimberly-Clark has also a high probability to increase, right? So this is something to keep in mind. I don't know if you have something, any question on this?
This was a great demonstration, very impressive. I wanted to understand, essentially what you're doing is you're using the sort of each pair.
Yeah, in this one, yeah. Mm-hmm.
Would specify the joint probability distribution. And so there's no memory, so it's basically co-occurrence. So
yeah. We are not, I don't know if it's your question, but we are not taking into account the time dimension in this case. So, because we have 459 time series, but in this example, I'm not using the time. We can use it, but in this one, we are not using it. So we don't care about, is it day 1 or day 254? We are just looking the co-occurrences.
Right, so these are essentially sort of your samples. We're assuming that along the vector, along the sort of row, we're essentially getting samples from a very large joint probability distribution of these 400, and with that distribution, the shape of that distribution is being characterized with this type of directed graph, or not even a directed graph.
Yeah, in this case, it's a graph, yeah, because even if we have direction, indeed, we don't have any direction at the end of
Right, right. Now, could you, I mean, just, and I know we probably don't have time, but if you had to extend that to a real-world situation where there's aspects of feature selection, where we don't really know, I guess, what those samples are that we care about, and then time. Are there any tools that would be available before this step that could take, I guess, the question is, let's say before there was balance sheet information for each of these companies. So you had stock price, but then you also happen to have income statement information or balance sheet, which expands the data set by a factor of, I don't know, 10,000. What could we then do as a pre-processing step to say price?
I will probably do this kind, for example, here I just took everything, right? So let's suppose now, if I want just to, I know I want to focus on P&G, for example, I can just define P&G as my target, right? And say, well, it would be the same thing. I have stock prices, I have lots of information about the number of employees and things like that. I just want to see what is useful for characterizing my variable. So I can go there and do what we call supervised learning in this case, right? And then I will be able to use what we call the augmented Markov blanket learning. And then it's just selecting among these 450 nodes what are, this is a feature selection algorithm, if you will, what is the Markov blanket of this node? So what is useful for characterizing Procter & Gamble? So if you have lots of dimensions and you don't know what is useful or not, you can always start with that just to see what can be interesting. So when we do, for example, gene analysis, we have 20,000 genes and one disease. And then, so we are not interested in finding all the relationship between the genes because this is not really useful, but we want to find what are the most important ones for being able to understand the disease.
Got it. Thank you.
Okay. No? Any other question?
No more questions?
Oops.
All right. Well, thank you very much, Lionel, for this presentation. I always love to I just love watching all those 500 nodes dancing around on the screen and the network appear almost magically. So with this very last example, we managed to go into even another aspect of our quadrant map where we talk about supervised learning. So there are actually countless more examples, way more than what we could share with you in this presentation today. You can go to our website, Bayesian.us, and there we have a section on tutorials where we are going through quite a number of case studies, everything ranging from bioinformatics. You'll see the where's my bag example, the stock market example, vehicle accident analysis, really covering a broad range of fields of study that I think highlight what Bayesian networks can do in many different areas. So with that, unless you have any further questions, I would just really like to thank you for joining us today. Thank you for your interest. We'll be around for a little bit, Lionel and I, so if you would like to ask us any questions offline, we'd be more than happy to answer those questions. I should also point out we have a trial version available of BayesiaLab. So if any of this interests you, you can go online, download the trial, download the data sets, for instance this one, and then have at it with your own trial version and experiment with BayesiaLab. I think you'll find it fascinating. I certainly was fascinated when I was first exposed to BayesiaLab 6 or 7 years ago, and I never let go. It's a really fantastic tool. So thanks again. Appreciate your interest, and hopefully we'll see you once again at a future event of this kind. Thank you.